So, ladies and gentlemen, welcome back. So today we will talk about how to simulate shadows. Now, as you see in these examples here, shadows are a very important effect which allows us to perceive in particular the spatial relationships between objects. Now, for instance, here in this example you see very nicely that we interpret the shadow in order to determine at which location relative to the ground or at which height relative to the ground the player is. So it is an important effect to give realism, a certain degree of realism to what we see or the image we create from a scene, and further it's a so-called visual cue that allows us to estimate the spatial relationships in a more accurate way. So shadow simulation is very strongly related to what we call visibility. So, and therefore let us just talk briefly about what we mean by visibility, and that brings us first of all to the depth test. So remember, or you hopefully remember, that the depth test, which we have introduced a few weeks ago, resolves what we call visibility on a per fragment basis, meaning that it determines for every fragment that wants to be rendered whether this fragment is visible, so whether it is closer to all the fragments that have been rendered before to the same pixel, or whether it's further away and should therefore be discarded. And in order to perform the depth test, we have introduced the Z buffer, a buffer which has the same size than the color buffer and just stores the minimum so-called Z values or depth values of all fragments projecting onto the same pixel. And during fragment processing, in the fragment processing stage, after the fragment shader stage, the fragments are then tested, or more precisely, the fragment's depth values are tested by comparing these depth values to the value that is stored at the corresponding pixel location in the Z buffer. Importantly here, so we have seen that the perspective projection which we perform preserves the Z ordering, and remember that we have said that this Z ordering needs to be preserved exactly for that so-called visibility testing, because we want the fragment that is in front of some other fragment also after the perspective transformation to be in front of that other fragment. Otherwise, we could not resolve visibility on a per fragment basis. And if a fragment now survives the depth test, the Z value or the Z buffer value is incrementally updated, meaning that the fragment, if it's closer to whatever has been rendered before, just writes its depth value into the Z buffer at the corresponding pixel location. It overwrites the depth buffer that has been stored before. Otherwise, the fragment is just discarded because it is occluded and not seen. And keep in mind that this only holds for opaque objects. We have also looked at what we have to do if we want to render transparent objects, and their color contribution should be blended in the correct visibility order then, in order to, in a physically motivated way, mix their colors. And keep in mind here also that the visibility was determined or is typically determined with respect to the viewer. So the viewer is the center of projection when performing the perspective transformation, meaning that the distance of the fragment, or the distance or Z ordering of the fragment, is with respect to their distance to the viewer, or to the view plane, which has been defined in a certain distance to the viewer. So here's the Z buffer algorithm in pseudocode. So what we do first is we initialize the color buffer and the Z buffer with some initial colors and values, with the background color, which might be black, and an initial Z buffer value or depth value that is equal to 1, so the largest value that can be stored in such a depth buffer entry. Let's assume that this is 1. And then what we do is we render the scene. No? So we render every polygon. Then the rasterizer generates fragments. The fragments are associated to a certain pixel location. These are the pixel coordinates x, y in the pixel raster. With fragment.depth, we can access the current depth value of the fragment. We have seen that this depth value is kept after the perspective transformation, so we can access it. And then we simply compare that fragment's depth value, the set value here, to the value that is currently stored in the depth buffer at that pixel location xy. And if the fragment's depth is less than the value that is currently stored in the depth buffer, then we incrementally update the Z buffer. We let the fragment override the Z buffer value at xy with its own Z value. We also let the fragment draw its color into the color buffer. And otherwise, if the depth test fails, the fragment is simply discarded, so it doesn't have any effect. This is how the Z buffer works. And now we want to look how this relates to shadow simulation. So we keep in mind here visibility tells us which objects can be seen from the viewpoint. And now if we look at shadows or shadow simulation, then we can say that shadows essentially need to know, in order to simulate shadows, we need to know which objects can be seen from the light source. So if we want to create an image of a scene, we want to know whether a fragment can be seen from the viewpoint, from the camera position. And if in addition we want to test whether a fragment is in shade or not, then we want to essentially answer for every fragment the question, is that fragment or can that fragment be seen from the light source? Then the fragment receives light from the light source, otherwise it is in shade. We see this here where we have a light source positioned here to the left. That light source illuminates the scene. And now we see if we pick a certain point, this one here or maybe this one, then we essentially, in order to determine whether the point is in shade or not, we essentially ask for the visibility of that point with respect to the light source. If the point, as the point which we have here, is visible from the light source, then of course it receives light, so it is not in shade. If the point, as the one here, is not visible from the light source, it doesn't receive light, so it is in shade. So now, how do we actually simulate the shadow or shadows by using the functionality that is given by the rasterization rendering pipeline? And this brings us to the most popular approach for shadow simulation, which is called shadow mapping. And the shadow mapping approach simulates shadows in two rendering passes. In the first rendering pass, the scene is rendered in the standard way, but with a light source position as the center of projection. So it rendered the scene from the light source position. And why do we do that? In that first rendering pass, we want to determine all the fragments which are not in shade, which are seen by the light, because if we know that, then in the second rendering pass, we can just render the scene from the camera position and now test each generated fragment whether it was seen or not in the first pass. So if we could keep the information that is generated here in the first rendering pass over to the second rendering pass, meaning that for all the fragments that are generated in that second rendering pass, we could tell whether this fragment was seen in the first rendering pass by the light source or not, then we can immediately use that information in order to tell in the second rendering pass whether a fragment is in shade or not. And if a fragment that is rendered in the second rendering pass was seen in the first pass, it receives light. It just maintains its color, so to say, and draws that color into the color buffer. Otherwise, it is in shade and its color is darkened. And the test we would then have to perform in that second rendering pass simply checks whether in the first pass there was a fragment closer to the light than the current fragment. Because that is essentially what the result of the first pass should be. It should tell us, by telling whether a fragment was seen by the light source, whether there was any other fragment closer to the fragment to the light source, and then it is in shade, otherwise it is not. So the question now is, how can we determine that information which needs to be created here in the first pass, and in particular then how can we keep that information so that it can be used in the second rendering pass. This brings us then to the classical so-called shadow mapping two-pass approach, which in the first pass creates what we call a shadow map, which is essentially a buffer, a two-dimensional buffer or two-dimensional texture in which depth values are stored. And in the second rendering pass, this shadow map is then used in order to determine whether a fragment that is rendered from the camera position is in shade with respect to the light source or not. So here's again an illustration, so to say, of what we do in the first rendering pass. So we have the light source position here. We render the scene as seen from the light source position. We also say, we say very often that we render from the light source POV, and POV means the point of view. And what we do here when rendering the scene, we store the distance of the closest objects to the light source, or more precisely the depth values for the fragments that are generated here in a two-dimensional map, the so-called shadow map. And this map is just a so-called off-screen render target. Why off-screen? Because we don't want to show that render target as an image in that first rendering pass, but we just want to store values in it. We want to store it somewhere in memory so that then in a second rendering pass we can access that render target and use it in order to decide whether a fragment is in shade or not. And so these depth values, which are generated here and then stored in that two-dimensional shadow map. Now these are just the depth values as they are generated when rendering the current scene from the light source position. So rendering is then with respect to the what we call shadow map image plane. That is just the image plane you select here in that first rendering pass when rendering from the light source. You also use a pixel raster here for that rendering pass. So everything is exactly the same regarding the settings you have to specify as we discussed it when going through the different stages of the rendering pipeline. The only difference here is that you say, okay, I don't want to render now from the camera position, but I define a different center of projection, which is the light source position. Then you render the scene, and the depth values which are created or which are generated then during rendering, they are stored in the shadow map. Or in other words, you just perform the rendering as usual, and you could imagine that at the very end, if the scene has been rendered from the light source position, you just grab the depth buffer content and you store that depth buffer into the shadow map as an off-screen render target, and you then use this shadow map in the second rendering pass. What is stored in that shadow map is the distance of every fragment from the shadow map image plane. So here these red arrows indicate, so to say, the rendering of the fragments of three fragments, the fragment here and the one here and the one here. They are rendered in that first rendering pass with the light POV or the light source position as the center of projection. And then what is finally stored in the depth buffer that is created in that first rendering pass are essentially the distance values that are indicated here by the gray arrows. Here we have an image of the shadow map in 3D. So we have a three-dimensional object, we have the light source. We have rendered that three-dimensional object now from the light source position. And now what we see here, that is the content of the depth buffer after the scene has been rendered. And this content is then just copied into an off-screen render target, and then it can be used in the second rendering pass in order to determine the visibility with respect to the light source for every rendered fragment. Yeah, this is then done in the second rendering pass, now, which we see here. So we render the objects now from the camera point of view. Now here's the camera position. We now render in the classical view. Again, we have our image plane here. We render the scene now by projecting all the fragments into that image plane with the camera position as the center of projection. And now, in addition to rendering the fragments, what we do is we test for every fragment whether the distance of that fragment to the shadow map image plane, which is essentially indicated by the red line here and indicated by the red line here for the second fragment, and is compared whether this distance is larger or less or equal to the value that is stored in the shadow map at the projected fragment position. And therefore what we have to do is, whenever a fragment is going to be rendered into the image plane, we first have to project that fragment into the shadow map image plane. That then gives us a projected position in that image plane from which we can determine the location in the corresponding shadow map. And then we can read out the depth value from that shadow map entry and compare that depth value to the distance of that fragment to the shadow map image plane. And then we can perform, so to say, the depth test in a fragment shader, which simply asks whether the distance of that fragment that is rendered to the image plane is larger than the distance that is stored at the corresponding projected pixel location in the shadow map. And if this is the case, then you know that the fragment is in shade. Otherwise, that would be the case for the second fragment here, the fragment is not in shade. Then you just use this information in order to change the fragment's color if it's going to be rendered into the image plane accordingly. So that is the shadow mapping algorithm, that two-stage method which uses two rendering passes. In the first pass, it generates the shadow map, and in the second pass, it uses the shadow map entries in order to determine whether a fragment is in shade or not. So what we have to do in order to create the shadow map that is shown here. So in that first shadow map rendering pass, we have to create the shadow map, and therefore we need to project the geometry into the shadow map image plane. And this can easily be done by just changing the model view transformation matrix accordingly. Because changing the model view matrix, and also, of course, using a different projection transformation, now not with respect to the camera position, but with respect to the light position. And that is shown here in the bottom. So here what we do is we assume in the vertex shader state that a vertex is in camera or view space, XE, YE, ZE, WE. These are the view space coordinates of a vertex, meaning that we assume here that the vertex has already been transformed by the model view transformation matrix. And now, let us assume that we want to project that vertex not into the camera image plane, but into the shadow map image plane. And meaning that we want to now perform the projection of that vertex using a perspective transformation that takes the camera position as the center of projection. Okay, and what we do for this, so the first thing we have to do is we have to bring the vertex. No? We have assumed here that that vertex here is already transformed by the model view transformation, and the model view transformation is the model view transformation with respect to the camera view. Meaning what we have to do now, we first have to apply the inverse eye or camera view transformation. No? Because we want to get the vertices from view space back into object space. Because once the vertex is in object space, then we can use the light view transformation matrix in order to transform the vertex into the light view space, and then we can perform the final light projection transformation, which essentially projects the vertex into the shadow map image plane. No? And therefore what we do is we first multiply the vertex by the inverse eye view matrix, so that now the vertex is in object space. Then we transform each vertex with a light view transformation matrix to transform the vertex into light view space. And finally we apply the perspective transformation with the camera position as the center of projection. No? And then we essentially have the final coordinates here in the normalized device coordinate space with respect to the light projection. Yeah, we call this the vertex to shadow map projection matrix SM. No? And all we have to do now, if we want to generate the shadow map, we just render the geometry as usual, and in addition to all the matrices we apply in the vertex shader stage to the vertices, we also apply these transformations here, so that now rendering is respect to the light position. Yeah, then of course we also have to dehomogenize the resulting coordinates, meaning that we take the fourth, the homogeneous coordinate, and we divide the first three coordinates through that fourth homogeneous coordinate. That is what we do here. This then finally, so to say, gives the normalized device coordinates. So all the coordinates now after this transformation has been applied are in that cube from -1 to 1 in all three components. And now we want to use these coordinates in order to access the shadow map, which is a texture. And this texture is accessed via texture coordinates, and we have said texture coordinates are always between 0 and 1. Now here, after this transformation here, the coordinates are between -1 and 1 in so-called NDC, normalized device coordinates, with respect to the light position. Okay, and what we now have to do in order to use these coordinates as indices or as texture coordinates into the shadow map texture, so we scale them by 1/2, at least the first two components. These are then the two-dimensional texture coordinates we use. So we scale them by 1/2. That brings the components from -1 to 1 now to -1/2 to 1/2. And then in addition we translate the coordinates by 1/2. That then brings the components to to values between 0 and 1. Meaning after that normalization of the coordinates, we are now between 0 and 1. And this means that these two components can then immediately be used as texture coordinates to look up the values from the shadow map. Yeah, so this is what you have to do in order to render the geometry as seen from the light source position. You just change the or you just add an additional matrix, that SM matrix, the vertex to shadow map projection transformation, and then whatever you render is not rendered with respect to the camera position, but with respect to the light source position. And the depth values, which are then finally created when rendering, these are then the values which are stored in the shadow map, and these are then the values which you can finally look up by using the texture coordinates we have computed here in the last stage by using all the different transformations before. So yeah, here you see an example how that looks, how the different intermediate results of shadow mapping look. So here on the left we have the scene as seen from the camera position. Then here we look at the scene now from the light source position. Here we now see the depth buffer content when the scene is rendered from the light source position. So here the more bright the values are, the more close they are to the view plane. The darker the values are, the further away they are from the shadow map image plane. Sorry. Then here you see the projected depths. That means now for every fragment, you see here we are looking now from the camera position or from the eye position, and you have encoded here in the pixel values just the projected depth values, meaning for every fragment you see here, or for every fragment that is created when rendering the scene from the eye point. What we see here in that bottom left image is just the distance of the fragment to the image plane, to the shadow map image plane, encoded as a brightness value. Then comes the depth comparison. Here now for every fragment it is tested whether the projected depth, which you see here, is larger than the depth value that is stored in the shadow map. And if this is the case, then the fragment is in shade, otherwise it is in light. And if you now use that depth comparison information in order to modify the color of the generated fragments as seen from the eye position, then you arrive at the final scene, and this is then what is finally drawn into the color buffer. Yeah. So let me summarize. Shadow mapping, the first pass, which is essentially rendering the scene from the light source, and the depth buffer after that first rendering pass is then stored in a texture map. This is what we call the shadow map. A little bit about how this is realized in DX, the graphics API DX. Now, this can simply be realized by a pixel shader that computes the fragment's depth values and write these values into a texture resource instead of a color buffer. So, meaning, and we have seen this in some of the shader codes we have looked at. Without that, we went into further details. But you can imagine, because you can control all the transformations that are performed in both the vertex shader stage and also in the pixel shader stage. It is clear that now once a fragment is generated, you can just compute in a fragment shader the depth value of that fragment with respect to the current image plane. And the first rendering pass, that is the shadow map image plane. So that depth value would usually be generated by the rasterizer, but of course you can also compute that depth value in a fragment shader, and then you can just write these values into a texture resource buffer instead of the color buffer. Yeah, and therefore what you have to do, you have to, this texture resource here, you have to set up a description for that texture so that, so to say, the system knows that a texture of a certain type is now existing as a temporary resource in a memory segment. Then the texture is created, and finally you can simply use that texture as a so-called rendered target, meaning that whatever you render is then going into that texture. So the texture is essentially a copy of the color buffer, so to say, and now whatever is drawn is just redirected into that texture so that finally the resulting depth values are stored there. Yeah, and the so generated texture can then be made accessible to a pixel shader in the second rendering pass. In the second rendering pass, once you have the fragments projected into the shadow map, you have then read the values from the corresponding location from the shadow map and compare that value to the fragment's projected depth. Yeah, that is done in the second rendering pass. A pixel shader now computes the fragment's distances to the light source. So that is shown here essentially. So here we see two different fragments. Let us assume that is a fragment here, a point in 3D space. We have said that a fragment is in fact a surface point which is seen through a certain pixel, through the pixel here. And now what is done? So the distance of that fragment to the shadow map image plane, that ZB value here is computed. And then this value is compared to the ZA value here, which is the value that is stored in the shadow map at that projected fragment location. And if that ZB value is larger than the ZA value, then the fragment is in shade. Otherwise, and this is what we have here, the fragment is in light and it is not darkened. Yeah, that is the shadow mapping algorithm, a two-pass rendering approach. And this already tells us something about the complexity of that shadow mapping algorithm. It means simply that the scene has to be rendered twice for every light source that is given. If you have multiple light sources, if you have 6 light sources, then you have to create 6 shadow maps, meaning that the scene has to be rendered 6 times, with each of the light sources being the center of projection in one of the 6 rendering passes. For each rendering passes, you then store the corresponding shadow map. And then in the final rendering pass from the camera position, you have to test every fragment against all the 6 generated shadow maps in order to determine whether they are in shade and then alter their colors accordingly. Yeah, so that is again now an image here of the shadow map here on the left hand side, the shadow map as it is generated here in the first rendering pass for the scene we see here on the right. So the light source position is here. We are rendering now, we are looking now down at the scene, and we render the scene as seen from that perspective. And this then creates the shadow map we see here on the left. And the depth values in the shadow map, here indicated by the yellow bracket in this example, they are then compared to the depth of the fragments to the light source, and depending on that depth comparison, it is determined that a fragment is in shade or not. Yeah, a little bit about the shadow map implementation. So yeah, what we have to do is we have to set up the vertex to shadow map matrix SM, this matrix which we have introduced before, to transform a position from camera space into light space. So we typically set up this transformation matrix as an additional shader variable. And then what we can do in a vertex shader, we transform each vertex additionally into light space by using that vertex to shadow map matrix SM, as we have shown on one of the previous slides. And then in a pixel shader, what we can do, we can perform the dehomogenization of the light space coordinates through division by W. That was what we have also shown on the previous slide. We scale and translate so that now the transformed coordinates are all within 0 to 1. And the first 2 coordinates of the resulting transformed components can be used as shadow map texture coordinates. And what we then do is, then we sample by using from the shadow map, which is stored in a texture map. We sample by using these shadow map texture coordinates from the shadow map and compare the values which are looked up from the shadow map to the fragment's light space depth, which is simply the Z component of that fragment after the vertex to shadow map transformation matrix has been applied, and then dehomogenization by division through the homogeneous component W has been performed. I've made here explicit that we sample from the so-called unfiltered shadow map. Unfiltered means that we do not use bilinear interpolation in order to retrieve or in order to look up the values from the shadow map here. That means that we do not interpolate between the depth values which are stored in the shadow map when looking up the texture value by using the computed texture coordinate. So the reason is simply that, these values, if you look at a little, so to say, shadow map, which we have here, a 3x3 shadow map, and the real values which are stored here indicate the distances of the fragments that have been generated as seen from the light source position to the shadow map image plane. And now you can imagine what happens. So these distances, for instance, they correspond to different objects. So an orange, a reddish object and a greenish object, and they leave depth value footprint, so to say, in the shadow map. And now you can imagine if, for instance, I want to look up the texture value here at this location, and I would then bilinearly interpolate between the four depth values which are stored in the, so to say, surrounding of that texture coordinate, meaning that I would apply bilinear texture interpolation here. I would essentially smoothly interpolate these depth values, and what I would implicitly do by this, I would essentially assume that there's a smooth transition between the green object and the reddish object in object space. I would essentially create depth values which are not existing, because these objects might be far apart from each other, and in between there's nothing. But if I now interpolate the resulting depth values, I, so to say, create an artificial continuation between these two objects which are not there. And therefore, I look up the texture values from the depth buffer by using an unfiltered texture view, or let me become more precise, I'm just performing nearest filtering, meaning that I let the texture unit determine the closest texel to the current texture coordinate, and the value of that texel is then the value which I retrieve. And the lighting calculations, which I typically perform in a fragment shader, like the evaluation of the Phong illumination model, they only have to be carried out if the depth value is less than the value stored in the shadow map. So if the fragment's depth value is less than the value stored in the shadow map, because only then the fragment is visible, only then it receives light, only then the lighting calculation has to be performed. Otherwise, it is just rendered as some dark gray or whatever. As I've already said before, a little bit about the complexity. It requires, shadow mapping requires one additional rendering pass per light source. I have said this already. Shadow mapping can be used with point light sources and parallel light sources. If I have a parallel light source, then I do not use a perspective projection, but I use an orthographic projection instead of that perspective projection, and all the rest is exactly the same. So I simply have to exchange the projection transformation matrix. And there's another thing we have to consider, and this has to do with the resolution of the shadow map. I think it is clear if the shadow map has a rather low resolution, and because I'm performing texture lookup using nearest filtering, I have severe blocking artifacts, and that is exactly what you see here, for instance, on the left-hand side for a texture map of resolution 1024 by 1024. And it's clear that these blocking artifacts, of course, are an effect, a direct effect of that unfiltered nearest texture lookup. No? But we have seen we need to do this because if we would apply bilinear interpolation, then we would essentially create artificial geometric structures which are not existing in the scene. It is also clear that I can essentially make these blocking artifacts appear less strongly by just increasing the shadow map. But it should also be clear that this is of course not a general solution, because in order to make these artifacts completely appear, I would have to use such a very high resolution of the shadow map that it explodes, the memory consumption explodes, and meaning that this approach is not always practicable. And we will see in the image synthesis lecture in the winter term, we will see other techniques which can avoid this kind of blocking artifact in shadow maps. And we will also look at alternatives to shadow mapping, which can also simulate shadows, but entirely can avoid these blocking artifacts, but at the same time come with other disadvantages which shadow maps do not have.